Hello there. Welcome to section 4.2, null spaces, column spaces, and linear transformations. Applications of linear algebra require subspaces of Rn, and these applications are going to appear in two ways. The first one is the set of all solutions to a system of homogeneous equations. And the other is the set of all linear combinations of the vectors. And what we're going to do in this section is compare and contrast these items. And you will find that this is basically the same things that we've been doing, just again, new terminology. So let's get started. The first thing we're going to talk about is the null space of a matrix. So previously we talked about homogeneous systems that deal with this equation here. And what we wanted to do was find the solution set. Well, this leads to what is called the null space. The null space of an M by N matrix is the set of all solutions to the homogeneous equation AX equals 0. So it's the same thing we've done, but new terminology. And the null space of matrix A is represented in this manner here. So another way you can think of it is the set of all vectors mapped to the 0 vector by this linear transformation. So let's take a look at a concrete example here. So we have a matrix A and a vector U, and we want to determine if this vector U belongs to the null space of A. Well, in order to figure that out, what we will do is we will compute AU equals 0. And if we end up with the 0 vector, then vector U is in the null space of A. So we will go ahead and find AU. So we're just multiplying here. So when we multiply this, our first row is 5 minus 9 plus 4. Then the second row is negative 25 plus 27 minus 2. And sure enough, this results in the 0 vector. So this tells me that vector U is in null of A. Why don't you go ahead and try this one? So pause the video and come back. So again, if I want to figure out if vector W is in the null space of A, I want to compute AW, and if that equals 0, then yes, it is in the null space of A. So when you find AW, you do in fact end up with the 0 vector. So this tells us that vector W is in the null of A. Not so bad. So for a moment here, let's flash back to section 4.1, where we talked about subspaces. And remember, a subspace of V is a subset of H that satisfies these following properties. So, Theorem 2 in this section says that the null space of an M by N matrix is a subspace of Rn. So this will come up in your homework. Basically, if you have an M by N matrix, the number of columns will help you identify the subspace. So if this is a 3 by 4 matrix, the null space is a subspace of R4. So in this section, you will see information about implicitly describing and explicitly. And in this example, we want to explicitly describe null of A. And in order to do that, we will write a solution set in the parametric vector form. Again, stuff that we've already done. So by solving AX equals 0, this will produce the explicit description of null of A. So suppose we have some matrix A and we can reduce it to this. Remember that from this matrix you can write a general solution. And from that general solution, then you can write your parametric vector form. Okay, so I'm assuming you remember this. If not, make sure you review it. Remember that this represents, say, vector u, this represents vector v. Well, this can be represented then as x2 u plus x4 v, and this is a linear combination of vectors where the weights are the free variables. So from this, it's important to mention that every linear combination of vector u and vector v is an element of the null space of A, and vice versa. So UV is a spanning set for null of A. And I'll provide you all of this information here in a little bit. But let's look at another example of this. Okay. So we want to find a spanning set for the null space of this matrix here. So what we want to do is we want to find a general solution for AX equals 0. And what we will do is we will row reduce the matrix A0. So remember, A0 is matrix A with a 0 column. Okay, so if I row reduce this, I'm waving my hands here just for the sake of time. If I row reduce this matrix here, I will end up with the following matrix. Cue elevator music. Okay, so I end up with this matrix. All right, so let's kind of review what this tells me. I have some pivots here and no pivot here, here, and here, which means these are my free spaces. So remember from this, x1, x2, x3, x4, x5, I can come up with the following general solution. x1 minus 2x2 minus x4 plus 3x5 is equal to 0. Then x3 plus 2x4 minus 2x5 is equal to 0. And then I have a row of zeros, so 0 equals 0. Okay, so from here, remember that we can set up the following. So if I solve this for x1, I end up with 2x2 plus x4 minus 3x5. x2, remember, is free. x3, if I solve this for x3, I have negative 2x4 plus 2x5. x4 and x5 are free. Okay, so now from here, what we will do is we will pull out our weights, so like the GCF essentially. So x2, and then all the coefficients of x2 are 2, 1, negative, 2, 1, and then the rest are zeros. Do the same for x3. I'm sorry, there is no x3, that's free. Do the same for x4. x3 is not free, it's just not right here. Sorry, I got distracted. Okay, and then x5. Negative 3, 0, 2, 0, 1. Okay, so from here, this represents vector v, vector w, let's do x, w, and x, good Lord, v and w. Okay, so we can represent this in this way. So what this tells us is that every linear combination of x, v, and w is an element of null of A, and vice versa. So x, v, w is a spanning set for null of A. And that answers that question. So now we're going to step away from the null space for a moment and talk about the column space of a matrix. The column space of an m by n matrix, and that's denoted in this way, is the set of all linear combinations of the columns of A. So if A equals this, then the column of A is the span. So in other words, the column A is equal to vector B such that B equals AX, so this equation that we've seen a million times, for some X in Rn. This leads to a theorem that we will see very frequently, and it's very similar to the first theorem, but now referring to the column space of an m by n matrix, the subspace is RM. So if you have a 3x4 matrix, the column space is a subspace of R3. The null space and column space are two of the four fundamental spaces that we will talk about associated with a matrix. So let's see this in action. Okay, so here we have vector U and matrix A, and we want to determine if this vector is in the null of A. So remember, in order to do this, we will verify, verify that AU is equal to the 0 vector. So I have this 3x3 matrix here. We will multiply it by this matrix, rows, columns, and sure enough, you end up with the 0 vector. So as we discussed previously, if you end up with the 0 vector in this case, then vector U is in the null of A. Okay, well now we have something new. So now we want to determine if this vector is in the column space of A. So in order to figure this out, what we will do is we will reduce AV and determine if the matrix will produce a consistent or inconsistent system. And if it is consistent, then the vector is in the column space. If it is inconsistent, then the vector is not in the column space. Okay, and this all stems from our discussion in previous sections regarding linear combinations. Okay, so this is the following. Okay, so then I'm going to add a column here, which is vector V. And I'm going to row reduce this. And, you know, at this point, however you row reduce is fine. When I row reduce this, I end up with the following matrix. So at this point in the class, I'm concerned that you know how to interpret what you get after you reduce. Okay, so looking at this last row tells me that this is inconsistent. So because this is, once it's reduced, we have an inconsistent system here. Vector V is not in the column space of A. Let's look at another example. Well, I've talked about this a little bit, but here we have this matrix A, and we want to determine if the column space of A is a subset of RK, what is K? And then the same question for the null space. So this is quite simple to figure out. What you need to do is identify the dimensions of this matrix. And this is a 3x4 matrix. So the column space that deals with theorem 3. And we talked about this before. So we want to find how many columns there are, rows. how many rows there are, and that will help us determine our subspace. So it will be R3. Then part B, the null space, is theorem 2. This here will tell us what our subspace should be, and this one is R4. So K equals 4 and K equals 3. Not so bad. In this example, we have the same matrix, so just keeping it simple. And in part A, we want to find a non-zero vector in column A. Well, if I want to find a non-zero vector in column A, basically any of these columns will satisfy this question. So any column of A, pick one. The book picks the first one, I'll pick the second one. Okay. Now, in part B, now we want to find a non-zero vector in the null of A. So if I want to find a non-zero vector in null of A, remember that we are going to row reduce A0. So A0, I'm actually going to do it up here to save some space. This, I'm waving my hands, and again, remember that this is matrix A with a 0 column. When I row reduce this, I get the following matrix. All right. Okay, so remember the next step here, from here, what we want to do, now that we have this reduced matrix, it would be helpful to identify our pivots and our free spaces, or free variables, whatever you want to call them, and then write the general solution. So our general solution is x1, and I'm going to solve for x1 because we're big kids. I think that we can handle it. x1 is negative 9x3. x2 is 5x3. x3 is our free variable, and x4 is just 0. Okay, so what we'll do, since we want to find a non-zero vector, what we're going to do is we're going to assign our free variable something. It can be whatever you want. So because we're just finding an example, there are lots of different possibilities here. So I'm going to assign x3 to be equal to 1. So anywhere I see x3, I'm going to replace it with 1. So one example of a non-zero vector in this particular problem would be x1 would give me negative 9, x2 would be 5, x3 we have assigned to be 1, and x4 is 0. So this is a non-zero vector in the null space of A. Moving right along. Okay, so here, same type of thing, but we're going to look at it a little bit differently now. So we want to determine if vector u is in the null of A, and then we're going to turn around and try to figure out if it can be in the column space of A. So we have done this a lot of times. So first, let's start with null of A. So remember, with null of A, we want to, so this is null of A. We want to find AU, and if it equals the 0 vector, then it's in the null of A. So I'm going to wave my hands a little bit just for the sake of time. when this is computed, we actually end up with this vector here, which is not the 0 vector. So this tells us that vector u is not a solution of ax equals 0. So u is not in the null of A. Okay, and this is the first time we've seen that case, so quite interesting. Okay, so now we want to see if u can be in the kernel space of A. Well, vector u has 4 entries. And if vector u has 4 entries, I want you to take a look at something here. This is a 3x4 matrix. And remember the column space of A is a subspace of R3. So if U has 4 entries, it cannot be in the column space of A, since the column space of A is a subspace of R3. So I'll write that down. Okay, so since there are 4 entries, this vector cannot be in column of A, since column A is a subspace of R3. Okay, so this is just too big. Okay, well, let's take a look at another example. So now we're going to refer to vector v, and we're going to kind of flip-flop. So first, we want to determine if v is in column space of A, and then if it's in the null of A. So in this case, when we're talking about the column space, we don't have to worry about our worry in the previous problem, because this satisfies theorem, what is it, theorem 3? So we're good to go. So remember, for the column space, we will reduce matrix AV to echelon form. So AV, when it's reduced, becomes the following. It's kind of a big one, so hold your horses. Okay, so we have this. Now looking at this, just by observation, we can tell that this is consistent. So this is consistent. So vector v is in the column space of A. All right, so could v be in the null of A? Well, now it's similar to the situation we had here. Since there are 3 entries and A, null of A is a subspace of R4, no. So with only 3 entries, V cannot be in null of A, since null of A is a subspace of R4. Too small. Okay. The next several slides is really a bunch of reading. So here, as mentioned at the beginning of the video, we will compare and contrast the null space and column space. So this slide here basically does that for you. I think this will be helpful. Then the section goes on to talk about the kernel and range of a linear transformation. So before we talked about linear transformations on Rn, and now we're going to kind of focus this in on specifically vector spaces. So a linear transformation T from a vector space V into a vector space W is a function that assigns each vector a unique vector such that these things occur. Nothing crazy. Again, it's the same stuff we've seen, just different terminology. You'll see the word kernel, and basically a kernel of a transformation is the set of all vectors such that t of x is equal to 0. Then the range is the set of all vectors in W of the form t of x. Basically, you will find that kernel is just another name for null space, and range is another name for column space. It's just new terminology. And that wraps up this lesson.